Today we will find out all about this graph and why we are getting a couple of little dips, as well as looking at the trends in ionization energies and linking that to the periodic table, and then identifying an element from its successive ionization energy data. Then a quick reminder to download the free PDF so you can be making revision notes as we go along. The link is in the description. Alright, so before we look at this more complicated looking graph, let's go through the general trends in ionization energies and linking that to the periodic table. So linking first ionization energies to the periodic table. So the first thing we need to look at is that we are getting a general increase in the first ionization energy as we're going across the period. So this is like period 1, period 2, period 3. So we can see we're getting this general increase in the ionization energies. So this is because the effective nuclear charge is increasing as the shielding effect stays the same. So if we can remember the example in the last video of lithium and fluorine, the valent electrons in fluorine experience a greater nuclear charge compared to that with lithium. So lithium over here, it's one outer shell electron experience an effective nuclear charge of +1. Then we've got fluorine over here, that experiences an effective nuclear charge of +7. So the outer shell electrons are experiencing this greater effective nuclear charge. So click on this link here to find out a more detailed explanation about that. That's what we were doing in the last video. Then as we go down a group, so we've got lithium, sodium and potassium are in the same group, they're in group 1, so going down the group, also going down group 18 as well. Going down the group, the ionization energy is decreasing, and this is because the atomic radius is increasing. So as the valent electron is further away from the nucleus, it has less effect, so the positive power of the nucleus can't hold on to the outer shell electron as well. So this is why we're getting this decrease as we're going down the group. So this is down group 1 and then down group 18. So again, click on the link to find out more. But what we're going to be looking at today in a lot more detail is why we're getting these little dips. So we do have like the general increase, but we can see we're getting some little dips going down, and again, some little dips going down. But why are we getting these dips? So this observation provides evidence for the existence of the sublevels and how the electrons fill the orbitals. And we went through this in a lot more detail in an earlier video. So if you need a reminder about the electron hotel, then click on this link. So focusing on the period 2 elements, so we're just going to focus on these elements here in our next graph. So we can see that we are getting the first dip with boron. And this is because boron's most outer electron is in a p orbital. So this set of orbitals is slightly further away from the nucleus than the s orbitals. So it experiences a slightly smaller electrostatic attraction, therefore making it easier to remove. And then also the p orbitals. So the p orbitals are at a higher energy compared to the s orbitals. So again, because this orbital is at a higher energy, less energy is needed to remove this electron. Less energy is needed to remove that electron compared to if we were just removing a 2s electron. So this also happens with period 3 as well. So we can see we're getting a dip here with the period 3 elements. So just to kind of go through this again. So boron, its last electron, its valence electron is in the p orbital. Because we've got this gap in energy, it therefore just makes this electron a bit easier to remove compared to the 2s electrons. So now moving on to our second little dip. So here's our second little dip. In fact, move over here because we've got another more information on the side here. Yeah, so we've got our second little dip, and then you're kind of looking at oxygen. So it'll be easier to understand with what's going on with oxygen if we compare oxygen's electronic configuration with nitrogen. So that's what we've got over here. So the easiest electron to remove from oxygen is, yeah, this electron. So it is an electron coming from a full orbital. So yes, electrons do have opposite spins, and this helps them overcome the repulsion that they experience from being in the same orbital, but they're still forced to share an orbital. So if we can remember the up and the down representing the different spins, they're in the same orbital, but yeah, the electron-electron repulsion is still there. Yeah, so this is why, yeah, this electron is easier to remove. So electrons don't like sharing their room in the electron hotel. So if we compare this to nitrogen's p orbitals, so comparing this to nitrogen where all the p electrons are unpaired, yeah, more energy is going to be needed to remove them. So all three of these electrons are at the same energy, and it's going to be harder to remove one compared to this electron with oxygen, which is easier to remove. So therefore that's why this electron has this electron has a lower first ionization energy, and that's why we're getting the dip with the graph. So now we know we have the dips, we can work out which group every element is in. So going into the first dip, then this element has to be in group 13, and yet this observation supports the idea of the sublevels. Get back over here, so this idea supports the idea of the sublevels, and we're getting the difference in energy between them. Then going into the second dip, this element has to be in group 16, and this observation supports the idea that electrons fill empty orbitals first before they pair up. And then it's the paired electron that is slightly higher energy, so it's a little bit easier to remove. So even when we don't have this full lovely labeled graph as we do here, so we've got all of the elements labeled and their atomic numbers labeled at the bottom. So even if we don't have that, we can still figure out which group the elements are in. So so being able to understand this graph and being able to figure out which group the elements are in is a popular exam question. So let's just have a quick look at one now. So which element belongs to group 14? So we've got 3 elements going up before we're getting our first dip. So we know that this has to be group 16. So this has to be 15, and then this has to be 14. So we know that element B is a group 14 element. Hopefully nice and straightforward. Okay, so the final thing we can do with ionization data is to see how the number changes as we successively remove all the electrons from one gaseous atom. So let's see how these equations look. So with lithium, so this is the equation for the first ionization energy. So gaseous atom, gaseous ion plus the electron. Then the second ionization energy, so we can see we're already starting off with the ion, and again we're losing 1 electron. And then the third ionization energy is always 2 plus, getting a 3 plus ion, and then again we've got the electron. So the key thing is each time you are only ever removing 1 electron. So something like this. Would not be the third ionization energy, so this would not exist. It is only what we've got up here. Okay, so when you get all of this data from one element and plot it on a graph, it supports the idea of having the main energy levels. So let's have a look at our graph. So first things first, let's look at the graph's axis. So the first thing we need to take into account when looking at this graph is noting that the y-axis is using a log scale. And this is to take into account just how big the numbers are getting. So as the energy to remove successive electrons increases, this is increasing hugely. So the number is getting so big because each remaining electron is feeling a bigger electrostatic attraction to the nucleus. Then what we've got on the x-axis is the number of electrons removed. Okay, so now that's what the graph is. So now let's go on to explaining it and explaining why we've got this line. So the first thing to notice is we are getting some big gaps. So we're getting like a big gap here and a big gap here. And these big gaps are the most important thing. So each big gap is representing a move to the next main energy level. So you can figure out which element you have from looking at how many electrons are removed before you get that first big jump. So here we've only got one electron. We've got one electron and then we're getting our first big jump. So this has to be a group 1 element. So it's sodium, and yeah, we've got sodium over here. So the one electron is removed. Then we've got the big gap over here as we go down to the next main energy level. Then we've got our 8 electrons here, and these are the 8 electrons that are getting removed along here in n equals 2. Then we're getting another big jump, so another big jump, and then our final 2 inner electrons are the last to be removed. So you will have to identify elements like this by not only using a graph, so not only by using a graph, or more importantly, only like part of the graph, but also by looking at ionization energy data. So the idea is still the same. You're looking for the big gaps. More importantly, like the first big gap over here. Because how many electrons you have for the first big gap tells you the group that the element is in. So let us look at an example, like a data example. So we've got some ionization energy data. And then from this we can figure out what group the element is in. So again, we're kind of comparing the gaps, and we're finding out looking at which gap is the biggest. So between 2 and 3, that is the biggest gap. So because that's the biggest gap, we must have 2 electrons in the outer shell before we're going down to the next shell. So this would have to be a group 2 element. And and that's all there is to it. Nice and easy. Okay, so that's everything from me today. If you have enjoyed this video and want more IB chemistry content, then please do like, subscribe, and maybe tell a friend in your chemistry class. And if you want one-to-one chemistry help from me, then check out my website. The link is in the description. Catch you in the next one.